and is currently a postdoctoral fellow in the Department of Epidemiology. She'll be joining the faculty at the Stanford University School of Medicine this fall. So please join me in welcoming Maya.
Great, thank you. I'm very excited to be here. And I'm going to be talking today about some work on how to deal with publication bias in meta-analyses. And this is work that's co-authored with Tyler Vanderwill, who you all know well. He unfortunately can't be here today because he's giving his own talk right now at Longwood. So in any case, this is a work in progress. So I'll be especially eager to hear your comments, feedback, suggestions, and feel free to stop me along the way with those things as we go. So the general problem that we're interested in is that meta-analyses are often compromised by publication bias, selective reporting of results, or p-hacking. P-hacking usually refers to the situation where you sort of fit the model specification in different ways until you kind of get the p-value that you want. And so all of these things I'm going to refer to in aggregate as publication bias. So what we wanted to do is consider how severe publication bias would have to be to explain away the effects of a meta-analysis, or to shift them to some smaller value. So just broadly, the proposal that I'm going to be showing you is to consider a publication bias process in which studies that have results in the positive direction and with statistically significant p-values that are less than 0.05 are some ratio more likely to be published than studies with either negative point estimates or results that are not statistically significant. And we assume that we don't necessarily know that ratio, but that we could conduct sensitivity analyses across different choices.
What's the population that you would like to infer to?
Yeah, so basically like all the studies that have been conducted but not necessarily published. And so that also encompasses things like if investigators fit a model and then it looks like it's not good, and so it doesn't even make it to being written up as a paper.
But isn't most of the selection, I mean, some of the selection may be, p-hacking and, bad behavior, basically. But isn't in most of it, sort of honest, hardworking scientists, like trying to find something newsworthy, right? Like, if we did this to the New York Times, it would be really boring to read, right? And same thing with the scholarly literature. So, like, it would be really interesting to know what the population is, because I don't want to look in people's file drawers. Most of that is just mistakes and irrelevant stuff. So, how do you identify the population?
Yeah, so I think we're going to see this a little bit more closely when we look at the model, because we're specifically considering selection that's based on the p-values. So we're not interested in kind of selection that happens for other reasons. So there are certainly reasons that studies get chosen for publication based on being interesting or being impactful, and those are, I think, the kinds of things that you're referring to, and that's not what we're not trying to infer to the whole population of like everything that's ever been conducted. We're specifically focusing on removing the effects of selection that's specifically based on the magical p is 0.05 cutoff.
I mean, but isn't the magical p 0.05, I mean, there's a lot of selection which pushes for p 0.05 that's completely appropriate, right? Like you're looking through the telescope, and what do we want people to do when they look through the telescope? We want them to turn it up to 10 and stand on their toes and stick out their neck and squint and tell us about the thing that is just past p 0.05, right? So, like, that's what we want most of the time. I mean, if they're doing it honestly. Like, we don't want them to do it illegitimately. So can you separate those two things?
Okay, so I think if I'm understanding correctly, the issue is that, like, we don't want to publish findings that, like, we want to select for findings that are kind of interesting enough and with strong enough evidence that they do surpass that threshold. Is that kind of what you're saying?
I think, I guess what I'm saying is there's a lot of selection mechanisms. You mentioned that you just want to focus on one selection mechanism, but it seems highly confounded with a really good selection mechanism. Like, there's a good selection mechanism, which is, keep looking through the telescope, turned up to 10 until you see like a planet with little green guys walking around. Like, I really want to know that, right? And then there's a bad selection mechanism where they're messing with the PowerPoint slide, the photoshopping of the thing to get the p = 0.05. And
Yeah.
can you, like, they're both pushing in exactly the same direction. So can you statistically, I mean, it's unfair for me to ask this question because you haven't shown us anything
No,
yet.
it's fine.
But can you statistically distinguish between these two?
Yeah, I honestly haven't really considered it that thoroughly. I mean, I think, yeah, I mean, I guess even if you're selecting for the small p-values in a way that's sort of honest, it is still going to bias meta-analyses in the sense that the point estimates that are getting from that selected set of p-values are still going to be sort of inflated compared to the underlying population of estimates of that effect size, which have not yet been selected for p-values.
But then it depends upon what the population is that we're referring to, right?
Yeah, I mean, I guess I'm just not sure how you would interpret sort of sort of what would be the scientific interest in like the point estimates that were selected for the small p-values. Because like with meta-analysis, we're sort of trying to infer something about that distribution of true effect, and so I guess I'm just not quite seeing what that population would represent compared to the population of all the estimates that have been produced prior to selection on the p-values.
I think we do our. I'm being totally self-indulgent. So let me let you continue now.
Okay,
I'll
no,
bother
I
you
appreciate
later.
it. I think I'm maybe just not quite understanding the question, so I'd love to hear more about that. Okay. Anyway, so we're considering a publication bias process in which the positive significant results are some ratio more likely to be published. And so then ultimately, what we're going to do is try to make statements like, in order for publication bias of this type to shift the observed point estimate to the null or to some other value, then those significant positive findings would need to be at least, let's say, 30-fold more likely to be published than the negative or non-significant ones. And so we could then think in practice whether that 30-fold is a number that's too high to be plausible for a given question and literature, or whether it's small enough that we think it actually could be the case. So there are a couple of existing methods, there are many existing methods to try to estimate or adjust for publication bias, and these fall generally into two types of categories. So the first is methods that are kind of based on the funnel plot, which is looking at the association between the point estimates and their standard errors. And so these basically consider publication bias of a form that operates on the effect sizes and that does not really operate on the very largest studies. So empirical evidence to date has sort of suggested that this is sometimes not the most realistic model of the way that publication bias actually operates. In fact, it seems like it operates more based on the p-values, especially based on that 0.05 cutoff, than on the effect sizes. And so an arguably more realistic class of models is instead consider selection that operates on the p-values and that affects all studies. And these are kind of broadly called selection models. So I like selection models very much. I always try to apply them in meta-analyses in applied work, but they do have some limitations. So the main one is that they typically require pretty large meta-analyses to work well and to give stable estimates of the severity of publication bias. And so with kind of realistically small meta-analyses, you may not really be able to do that much with these approaches. And then the other thing is that they typically do make parametric assumptions on the distribution of true effects that underlies the observed studies. And that's a common thing in meta-analyses, but it becomes especially tricky to assess whether those assumptions are plausible when you already have publication bias that's distorting the point estimate. So it's just hard to determine whether the latent population of studies follows any given distribution. Yeah, question?
Are you gonna tell us what those models are? Or?
Not in a whole lot of detail, because I'm going to be showing something that's kind of a different approach from selection models.
You only observe what's published, right? So you don't observe anything about what's not published?
Yeah.
So what kind of model is
Yeah,
a selection model?
So it's basically kind of a joint likelihood model where you have your usual likelihood for the true effects, which is usually normal. And then you also have a term that corresponds to basically a step function where your conditional probability of being observed is a function of whether your p-value is less than or greater than 0.05. So you end up with kind of like a second parameter that's the ratio of publication probabilities for significant versus non-significant. And then you kind of just do like a joint maximum likelihood kind of thing. So we're going to be considering an applied example that I think kind of nicely illustrates the fact that these existing methods, while useful, can sometimes lead to just a lot of uncertainty and debate. So this was a meta-analysis that looked at 75 studies and tried to estimate the association of playing violent video games on aggressive behavior. And it estimated a small effect with a pooled correlation of 0.16. Now, this was an interesting paper because this was published almost 10 years ago, and still to this day, there's quite a lot of debate about whether these effects are completely due to publication bias. And so there were commentaries where commenters fitted different sort of selection models or funnel plot models, and then the original authors responded, and there just was a lot of debate about whether these effects actually were sensitive or not sensitive to publication bias. And so what I'm going to try to show you when we go into reanalyzing this is that we think that sometimes our proposed methods can lead to clearer conclusions in these kinds of cases. And that's really because they try to shift the focus from actually estimating the severity of publication bias to conducting sensitivity analyses across a fixed range of parameters. So that's what we're going to hopefully see. So as moving into the sensitivity analyses, first I'm just going to flesh out the model of publication bias that we're considering. So again, we're kind of thinking of studies as being in two different categories. There are affirmative studies, which are the ones that are both positive and statistically significant. And then there are non-affirmative studies, which is negative or not statistically significant. And so we assume that the affirmative ones are, let's say, eta-fold more likely to be published than the non-affirmative ones. And again, this is a model that seems to conform fairly well to empirical evidence on the way that publication bias operates and the way that researchers and statisticians interpret p-values. So just as an example here, I just generated data. So this is a latent population of studies prior to inducing any publication bias. And so what I'm showing here is, this is sort of like a funnel plot in that it's the point estimates of the studies versus their standard errors. And I'm just differentiating with the colors between the non-affirmative and the affirmative studies. And so any study that's lying exactly on this line is one that has a z of plus 1.96. So then if I go to add publication bias, so this is with eta as 10. So what I'm doing here is basically cutting out, keeping only 10% of the non-affirmative studies and 100% of the affirmative studies to get that 10-to-1 ratio. So the model that we consider also assumes that publication status is independent of the point estimate conditional on a study's being non-affirmative or affirmative. So that's basically just saying that the non-affirmative studies that I observe are representative of their own latent population, and likewise for the affirmative studies. So essentially the publication bias process is really just selecting for that p is less than or p is greater than 0.05. And this model is also agnostic to the reasons for selection in the sense that it could be sort of any combination of p-hacking, selective submission of results by authors, selective acceptance of results by journals. All of these things can kind of be pulled together into the same model. And we're going to consider two different types of sensitivity parameters. So the first one is called eta of mu hat comma q. And this is just the severity of publication bias as operationalized by that ratio that would be required to shift my pool point estimate called mu hat to some smaller value called q. And I'm going to be talking about cases where the mu hat is positive, and so the q would be some smaller positive value. Everything still does apply if you have negative point estimates instead. And so for those of you who are familiar with the e-value, this is kind of a similar idea in that it's the severity of publication bias that would be needed to shift my point estimate to some value. If q is 0, then it would be the publication bias needed to shift my point estimate all the way to the null. And then we can also consider something analogous for the confidence interval. So we might want to know the severity of publication bias that would shift my confidence interval to include something, for example, the null for q is 0, or potentially some other smaller value. And so this is useful because if we had large values of these etas, that would suggest that the results are relatively robust to publication bias, and that it would take a lot of publication bias to actually explain away the results. And in contrast, smaller values would suggest that relatively small amounts of bias would actually explain away the findings. So I'm going to talk about 3 different meta-analysis specifications. They're all kind of nested within one another. So we'll go roughly from sort of least general to most general. So the first one is going to be the fixed effect setting. And that arises basically either if you assume that the true effects are do not have any heterogeneity, or if you really only want to draw inference to the observed studies that are meta-analyzed rather than to some broader population. So that's fairly restrictive, so we'll also consider two different random effects models that allow for heterogeneity in those true effects. So first off, this is just an uncorrected fixed effects model, so I haven't done anything with publication bias yet. So the way you get the point estimate is just you just take an inverse variance weighted average of the individual studies' point estimates, which are the theta i's. And then the variance is just the inverse of the sum of those weights. So pretty straightforward. So if we wanted to go ahead and bias correct this for a given value of eta, we could just do something similar to inverse probability weighting. What we could do is basically split the studies into the affirmative ones and the non-affirmative ones. And then for the non-affirmative ones, we could further upweight them by a factor of eta. And then not apply any additional weight to the affirmative ones. And then another way to think about this is that you could treat sort of this, the sum of the weighted sum of the point estimates in the non-affirmative studies as one quantity, which I'm calling y bar nu, and then the counterpart in the affirmative studies as y bar a. And you could think of this weighted estimator as basically weighting the joint contribution of the non-affirmative studies compared to the joint contribution of the affirmative studies. And this has a variance that's, also rather simple. And then these new terms down here are just the denominators that you would have for the non-affirmative versus the affirmative studies. So what I just showed you was kind of basically a means to an end, in the sense that we never actually know eta in practice, so it's not really that useful to try to bias correct for some unknown parameter. But what we really want to do instead is actually just try to solve for the value of eta that would be needed to shift my point estimate to some value. So here's what that looks like. It's pretty straightforward because, again, it's just a function of the fixed effects sum and variance of the non-affirmative and then of the affirmative studies. And for example, if we're interested in actually shifting all the way to the null, then what we end up with it is actually just the ratio of the fixed effects sum in the affirmative to the non-affirmative studies, the negative of that. And so what's kind of interesting about that is that, so like for example, if it were the case that the fixed effect sum in the affirmative studies is 5-fold larger than its counterpart in the non-affirmative studies, and in the opposite direction, then that's exactly the ratio of publication bias that I would need to explain away the results. So in other words, it would also have to be the case that the affirmative studies were 5 times more likely to be published than the non-affirmative ones. And then notice also that so if it were the case that the non-affirmative studies point estimate were actually in the same direction as the affirmative studies, then this would end up being negative, which is not possible because it's supposed to be a ratio of publication bias probabilities. And so what that means is that in that situation, there's actually no amount of publication bias under this assumed model that actually would be enough to shift the point estimate to the null. And we're going to see this again in practice. Questions so far?
So just is that partly that's a function of this assumption that the non-affirmative studies are representative of that population.
That's right.
So because you're just it's like you're truncating at the minimum possible, the minimum observed or not truncating, but you're basically saying I don't observe any negative effects or whatever. Then or they can't be. It can't be the case. There's not enough studies in that part of the distribution.
Yeah, so it's basically, we're going to see in a minute what happens as like eta goes to infinity, but it's going to go to the mean in the non-affirmative studies, and so it's not really the minimum, but it's rather their mean. But it is a function of that assumed model, because for instance, if there's selection even within the non-affirmative studies, let's say based on their point estimates, then that's not going to hold. So it does need to be that the publication bias is really just looking at this cutoff. Yeah.
So is the implication that if all the non-affirmative studies have positive point estimates that are insignificant, there's no publication bias that would make us
That would actually shift the
point estimate,
the bias corrected mean to the null.
Okay.
Yeah, and we're going to see this in one more slide also, so I think that'll help clarify the intuition. So there's also a closed form for shifting the confidence interval limit. It's kind of an ugly mess, but it does exist. So alluding to your question, we can also consider what happens under worst case publication bias, because that's the situation where eta is going to infinity. So in other words, the affirmative studies are getting to be infinitely more likely to be published than the non-affirmative ones. And so if that's the case, if we look at what happens to the bias-corrected mean, it actually goes to something that coincides exactly with the fixed effects mean within only the non-affirmative studies, without any correction for bias. And so what that means is that if you wanted to actually consider worst-case publication bias, you could actually just meta-analyze only the non-affirmative studies. And so again, with reference to your question, if those non-affirmative studies, if their own point estimate is still positive, then even if eta goes to infinity, we're just going to be upweighting that more and more heavily. So it's never going to get any worse than just the non-affirmative studies, again, under the assumed model of publication bias. So that's the fixed effects model. What happens if we want to consider, question?
For the fixed effect specification, how do you make inference about eta? Eta could be very large and unstable.
Yeah, so that's critical. So that's kind of why we're actually not trying to really do inference on eta. We're trying to solve for the value of eta that would actually shift our point estimate to some value. And you're exactly right. That's why selection models, as useful as they are, can be kind of tricky with smaller meta-analyses, because as you're saying, doing inference on eta is typically pretty uncertain. So moving now to the random effect specification, what happens if we want to allow for heterogeneity? So I'm going to be talking about one sort of more general model which has a special case. So we wanted to consider not only heterogeneity, but also allow for arbitrary distributions of true effects, so not necessarily normal. And we also wanted to allow for the case that the point estimates might be clustered, in the sense that it's often the case in a meta-analysis that some papers are contributing multiple point estimates, and we might expect those to be somewhat correlated. So I'm going to show you a model that kind of accommodates all of those things, and then a special case that is under independence. And this is going to look a lot like GE, so you'll see that it has many of the same properties. So just some notation, I'm going to let capital M denote the number of clusters, each of which has k sub m point estimates. And those point estimates are going to be called lowercase y. And then I'm going to let boldface Wm be a diagonal matrix of arbitrary positive weights for the studies in cluster M. And we're going to see that, like GE, we get consistency sort of regardless of this choice of matrix. But we're going to talk about how we choose it in this specific case. And then boldface 1 is a 1 vector, and boldface E is a vector of residuals for the studies in cluster M. So just the differences between their point estimates and the estimated mean. So first, just again, the uncorrected model. So the poor point estimate under the specification is doesn't really need to actually do anything special for clustering. It's still just a weighted average of the pool point estimates, but now it's using these arbitrary ways. And then the variance you can see kind of looks like GE in that it has this kind of sandwich term here that is basically a plug-in estimate of the covariance matrix. And then in practice, I'm not really going to show these forms on the slides because they're kind of messy, but in practice you can also apply sort of a finite sample correction to the variance, and that gives it nominal coverage even in arbitrarily small meta-analyses. And that was something that was important here in particular because as you weight the non-affirmative studies more and more, your effective sample size is basically the non-affirmative studies. So it really is important to have these things work without strong asymptotics. So if we wanted to go ahead and weight this, and then one other important thing is that, so again, like GEE, this is actually consistent regardless of the choice of W. And so it will give both unbiased estimates as well as correct inference, regardless of W. So if we wanted to bias correct this, again, for a specific fixed value of eta, we could do something similar to the fixed effects model with inverse probability weighting. And so again, we can choose whatever weights we want. What would make sense is to choose a product of weights for publication bias, which are the etas, with something that resembles the standard random effects meta-analysis weight. So what I mean by that is in a standard random effects meta-analysis, you are weighting the studies by the inverse of their total variance, which is their study's own variance, sigma squared I, and then also some estimate tau squared of the heterogeneity across the true effects. So when there's publication bias, it's pretty hard to actually estimate tau squared, and this model will not do it. So what you want to do in practice is sort of come up with some estimate of tau squared first, and then plug that into these weights. So what we actually recommend in practice based on simulations is actually just fitting just a totally naive parametric model to get some rough estimate of tau squared. That's going to be off because there's publication bias. It may also be off if the effects are non-normal. But again, because this is consistent under arbitrary weights, it actually doesn't really matter. We did also explore kind of weighting score contributions in a likelihood-based model to try to get a better bias-corrected estimate of tau squared. In practice, it's so hard to bias correct this with a realistically small meta-analysis that it didn't really change the efficiency. So all of this is just to say that it doesn't really matter. You can just choose like a naive estimate of tau squared, and this works just fine.
Are you assuming independence of a study's precision and its impact?
Yes, and it's point estimate, yeah. No, actually, no, we're not. Because, yeah, we're not because we're still just upweighting the studies that actually end up being non-affirmative. So it doesn't really matter if there's association there. You just can't have that the publication bias process is conditional on the point estimate once you're looking at affirmative versus non-affirmative studies. So if we were to consider point estimates that are independent, then the mean estimate actually stays the same, and the variance estimate just simplifies a little bit because we don't have to deal with clustering. So we still have our eta weight here, and then our regular random effects meta-analysis weights. And so for these two specifications, you can't necessarily solve analytically for the value of eta that would shift your point estimate or your confidence interval to a given value, but you can just conduct a grid search. So you can try different values of eta until you've moved the point estimate or the confidence interval to the desired value, and then you can use that as your estimate. And then once again, as we saw with the fixed effect specification, you can consider a worst case publication bias by only meta-analyzing robustly this time the non-affirmative studies. And this can sometimes lead to conclusions that are fairly compelling because sometimes it happens that you meta-analyze the non-affirmative studies and you still have a point estimate that's positive and of non-negligible size. And so that's a fairly strong argument that even if publication bias were extremely bad, you would still have some effect under the hood. Now, of course, in practice, if you actually have some non-affirmative studies to meta-analyze, it must be the case that eta is less than infinity. But it's still kind of a nice way to approximate the effects of really severe publication bias. And so empirically, we did a series of simulation studies on these three specifications. And so as expected theoretically, these are all unbiased, even under pretty severe publication, and they also do perform nominally in terms of inference, even with quite small meta-analyses and ones with quite a few non-affirmative studies as well. So let's go back to the violent video games and see what we can learn by adding these kinds of metrics. So here what I'm showing you is a plot that's similar to the one from before. This is a sort of a modified funnel plot that we think is sort of a useful complement to the quantitative sensitivity analyses. So as before, I'm distinguishing in color between the non-affirmative versus the affirmative studies. What I've added down here are two different fixed effects point estimates. So the black one is the fixed effects point estimate in all the studies, and then the blue one is among only the non-affirmative studies. And so the reason that's useful is that again, as we weight the non-affirmative studies more and more, basically the estimate that we observe is just going to be pushed more and more towards the blue one. And so if these two diamonds are close to one another, then that suggests that even under fairly severe publication bias, the corrected estimate is actually not really going to move all that much. And so you can kind of think of heuristically the sensitivity to publication bias as sort of how close or far are these 2 point estimates from one another. And one thing that's sort of interesting about this is that if you were to kind of interpret this plot as a standard funnel plot, because indeed it actually is plotting the same data, right? It's just the point estimates and their standard errors. Probably what you would notice is that there seems to be this correlation between the point estimates and their standard errors. And so typically a funnel plot based interpretation would be that this seems relatively sensitive to publication bias. But again, when the publication bias is operating on the p-values, that's not really the key consideration. The key consideration is really how close is the point estimate of those non-affirmative studies to the affirmative studies. Or I'm sorry, to the observed point estimate among all of them. And it turns out there's actually also cases that go in the opposite direction, where the standard funnel plot interpretation is that everything looks symmetrical and nice, but then if you actually look at the difference between these point estimates, they're actually very far away from each other, and maybe even in opposite directions, which would mean that if you have severe publication bias, your point estimate could even flip direction. So this is for the violent video games, and it looks like here, like these 2 point estimates are pretty close to one another. And so this kind of foreshadows what we're about to see quantitatively, which is that this meta-analysis seems to be fairly robust to publication bias.
Just
Yeah.
clarifying question. So in that plot, your model is assuming that the points in the purple, are a random subsample of a bunch of of a larger population where you have censorship. But that it's just
And non-affirmative.
that there's no other selection effects other than just sort of missing completely.
Right, so there could be like other, they could be getting selected for based on something like study design or something else, but it would have to be something that's not a function of the point estimates themselves. So it would break down, for instance, if studies' point estimates were a function of their study design and the literature selects for strong study designs, for instance.
Or maybe like a more like way that this would happen is that if they're selected for being like sharply close to 0, right? So like we publish null results when we know that like we don't publish noisy null results, but we do publish a lot of things that look like they rule out a lot of stuff that's not that's far away from 0. So we basically just and so that would this kind of like non-uniform way of doing things. You wouldn't be able to get the same results on. Right.
That's right, because that would be a form of publication that's conditional on the point estimate, even once you condition on affirmative versus non-affirmative. Yeah. So if that were a strong enough process, then that would affect the validity of these results.
Have you checked any of the non-affirmative studies? Did they report other significant findings? Like, how did they get published?
Yeah, so that's an interesting question. So in this case, I think they actually mostly this was kind of the primary finding. I think some of them kind of followed it up with things like subset analyses or something like that. Yeah, so I mean, I think in this literature, because this has been kind of a controversial field, I think that some of the null findings were published basically as null findings. But I mean, certainly there could be situations where it's not possible to publish something that's non-affirmative.
My thought is, if a study has a broader focus than whatever it is you're doing the meta-analysis on, it could be correlated with something that got over the 0.05 line, and so which means that you can end up with more non-affirmative studies near the 0.05 line than away from it. So it's still p-value centered, but because things tend to be correlated in your study, you got a lot of very violent people randomly in your treatment group by random chance or whatever.
Interesting.
So there might be an argument. I don't know. It might be an argument that you don't actually have a uniform censoring effect on that.
Yeah, no, that's very interesting. I haven't really thought about that, but yeah, thanks for bringing that up. Yeah.
So I have a different hypothesis for what the data generation process is. So I think if you have a reasonably good investigator, the probability of publication is 100%, essentially, because they will eventually get there.
They'll
However,
find a p-value less than 0.05.
they will publish it.
Somewhere.
No, 100%. That's a good point.
Yeah.
But they will change the quantity of interest, the test, the literature to which they're contributing to, the graph in your analyses, based upon what is going to get them published. Now, I don't know if that changes your results because,
Yeah.
but it's a different condition. I wonder if you modeled that, whether you'd get the same setup or whether there'd be a whole nother set of results.
No, that's really interesting. And then I guess the other thing I've been thinking about is that it could also be that it's more that publication bias delays certain findings from being published, in the sense that, like, you have to try, if you have a null result, then you have to try 10 journals instead of 1 journal. So in answer to your question, I guess another way to kind of make the sampling frame more specific is it's studies that have actually gotten into our meta-analysis. And so, for instance, if the investigators kind of change, so I mean, say they measure like violence, violent video games, aggressive behavior, and then 15 other outcomes, and some other outcome is the one that ends up being the selling point, then it may or may not be the case, depending on the way the meta-analysis is conducted, but it may well be the case that that study still doesn't make it into our meta-analysis because now it's been rewritten to focus on something else. But it does depend. I mean, in a really well-conducted meta-analysis, I would hope that, we're searching for terms that appear like anywhere in the abstract, or, so hopefully we're capturing all the literature that's actually measured that construct, but I think in practice, it's often the case that, like, if it's not the headline result, we can't really.
And the investigator probably would just delete it from the paper at some point.
Yes, that too. Yeah. So in general, I think that won't be a problem in the sense that those are just studies that are they're still not making it into our meta-analysis, even if they're sort of published. Okay, so let's put some numbers on this. So here up top, what I'm showing you is just uncorrected estimates from the 3 model specifications that I showed you, as well as on the second line, just a standard parametric random effects meta-analysis. The second one is basically just for comparison. And so across all of these specifications, they all point to basically point estimates between 0.15 to 0.18 on the Pearson's correlation scale. With pretty narrow confidence intervals, so kind of smallish effects, or at least associations of violent video games with aggression. And then if we take it all the way to the worst case, if we actually meta-analyze only the non-affirmative studies, what we get from all 3 model specifications is basically that the point estimates have been basically cut in half, so something more like 0.08. But again, it's interesting that these are still positive. So again, this is worst case publication bias. Even under these kind of worst case situations, we are still seeing at least there seems to be at least some sort of positive effect of video games on violent behavior. And again, with confidence intervals that are, indicating pretty small effects, but still probably positive.
Couldn't you easily come up with a more plausible worst case of estimating the number of researchers that would plausibly investigate this in the first place, and that would be your
So that would be like a number needed in the file drawer kind of metric?
Right, because you're saying that these are potentially studies that were embarked on and then abandoned. And it seems like you should be able to come up with a conservative figure. Or I guess, how quickly do you get towards 0.08? Do you need an R of like an R of a few thousand? Does that give you something?
Yeah, so let me actually show you. So it's kind of interesting because it's typically a pretty steep process. So for example, just to make it easy, we can look at the fixed effects model. So here I'm plotting the eta versus the corrected point estimate. So, I mean, it actually doesn't take a very large value. Like once you get to something like 40, you're pretty much most of the way to the eventual asymptote.
Great, so infinity is just as good as it.
Yeah. But that's interesting. I guess it sounds to me like what you're saying is sort of you could look at kind of the size of the latent population that you would need to kind of produce a given value of eta. Yeah. Interesting. Yeah.
Not that many researchers.
Yeah, that's interesting. I haven't thought about that, but that does seem like an interesting way to kind of reparameterize eta. Okay, So if we wanted to look instead at the, again, the publication bias that would be required to explain away the effects. So first in the first two columns, I'm looking at shifting the point estimate or its confidence interval limit to the null. And the NP here stands for not possible. So as we saw from the previous slide with these 0.08s, there's actually no amount of publication bias under this model that would actually shift either the point estimate or even its confidence interval limit to the null. Another thing we might do is maybe we can think about some smaller effect size. Like maybe we think that a correlation of 0.10 is kind of the smallest thing that we think is scientifically meaningful. So if we do that, we can again look at the severity of publication bias, the shift of that value, and we find that for the mean, it's actually still what seem like fairly large ratios. So for instance, with the random effect specifications, you'd need about a 30-fold publication ratio of affirmative versus non-affirmative studies to move the point estimate from the observed like 0.18-ish to 0.1. If you look at the confidence interval limit, it becomes smaller numbers. So probably a lot more plausible that we could shift the confidence interval limit to include 0.1. But I do think overall it seems to me to be a fairly compelling story in favor of robustness to publication bias in this case. That it seems like their point estimate doesn't really change that much until you really get into some fairly severe publication bias.
Actually, I like that NP is harder than NP hard. If you came up with a negative result, wouldn't that increase the probability of publication rather than decrease it?
I'm going to come to that in a minute. Yeah, so that is another possible model, and that we can accommodate that, but I'm going to talk about that, I think, in the next slide. Yeah, at the end of the next slide. So basically what we've shown is that sort of by trying to shift the focus from actually estimating the severity of publication bias to instead conducting sensitivity analyses across this fixed range of parameters, that we think enables fairly easy to report summary measures that can help kind of calibrate our confidence in meta-analysis. And the way they do that is basically by by avoiding trying to jointly estimate these fairly slippery parameters governing publication bias sensitivity along with the usual MLEs. It kind of buys us more flexibility in terms of what types of meta-analyses we can consider. Smaller meta-analyses, ones with fewer non-affirmative studies, meta-analyses with non-normal true effects, and situations like that. Okay, so now we're going to talk about the assumptions in the publication bias mechanism. So even though we've tried to relax a lot of the distributional assumptions that have been used to date in selection models, we do have this model of publication bias, and there are a few ways that this would not hold. So one of them is that, as you're saying, Gary, it's possible that there's selection in the literature for both positive and negative results. So it could be that a significant negative result is also upweighted in the literature compared to non-significant results. So we think that in a lot of cases, it's probably more likely that it's sort of positive results that are considered scientifically marketable. And so, for example, with the violent video games, there have been studies published that suggest negative results. It seems like the literature has in general kind of interpreted them in the same way as non-significant findings, and that there hasn't really been put forward a scientifically marketable argument for video games improving your aggressive behavior. So it seems like the literature has lumped them in the same category. Now, it's certainly possible that this actually does hold in some cases. And if that's the case, if you suspect that's the case, you can pretty easily modify these methods just by basically grouping the significant negative studies along with the affirmative studies. And so then the ones that get upweighted are just the non-significant ones. So it turns out that the assumption that we used in terms of what you might call one-tailed selection is conservative with respect to sensitivity analyses for the point estimate. In the sense that if you do the analyses that we showed as opposed to upweighting only the non-significant studies as opposed to both tails, then you will end up finding that the point estimate is more sensitive than it would look under the two-tailed selection. Note, though, that doesn't necessarily hold for the confidence interval limit. So confidence interval limit could be either way if you change the analysis, if you change the assumptions on the selection process. And then another thing that might happen is it could be that there actually are sort of multiple p-value cutoffs that get considered. Like it could be that marginally significant findings that are between 0.05 and 0.10 have some intermediate publication probability. It's also possible to sort of modify these methods. For that case, basically what you would do is have multiple groups of studies, each of which is potentially being weighted by a different eta. So there have been some pretty interesting empirical studies on the way that people interpret p-values, which kind of informed our choice to consider only one cutoff. And so, interestingly and soberingly, it seems that both researchers and statisticians alike essentially don't really distinguish very much between two p-values that are both above 0.05 or both below 0.05, regardless of where those kind of fall. So we think that probably considering one cutoff is going to do most of the work pretty well. You can also, so the one thing about trying to extend the methods to having multiple p-value cutoffs is that it is a little bit also less convenient in terms of sensitivity analyses, because now you have potentially multiple sensitivity parameters and not necessarily a unique combination. But you could potentially do that. And then sort of final limitation is that it could be the case that you actually have no non-affirmative studies. Like if the publication bias is just super severe, or if the true effects are really, really large, then you can't really do these methods, because you can't just upweight, non-affirmative studies that you don't observe. So you do need at least some of them to be in your sample. So just in closing, if you want a copy of the slide deck, it's publicly available. Everything needed to reproduce what will be in the eventual paper is also publicly available, or will be soon. And there's my email address if you want to contact me.
So I've seen a figure, at least in, I think, political science, where if you just plot all the p-values from the published studies, there's like a jump at 0.5 and maybe a smaller jump than 0.01. Is there a way to exploit that information?
Empirical estimates. Yeah, so we're actually we're doing a systematic review right now to try to look at to basically estimate parameters like that using existing selection models in the types of meta-analyses that actually are large enough to kind of give stable estimates, because I do think that's really useful in terms of interpreting these sensitivity parameters. Because the one thing that's kind of tricky is if I say, well, I came up with an eta of 30-fold. Well, it's kind of hard to say, is that plausible or not plausible? Like, I think intuitively for me, I don't really know the answer to that. And so what we're trying to do is basically empirically benchmark plausible values of eta across different disciplines, so that, hopefully that can help anchor your interpretation.
So just to follow up on this, it seems like one thing you could do if there's a real sharp cutoff is to do almost like a regression discontinuity design at the cutoff to at least get what is the value of P05, like P less than 05 at that cutoff, and then basically you could then kind of fudge about how much that impacts whether it declines with distance from p-value. That would at least give you some estimate of that would give you some estimate of eta to a benchmark for that particular that's in that particular study.
And I think the model would have to assume that RD estimate is true for everything else, because it's assuming that the ratio is constant.
Yeah, so we actually have played around with that, because the other thing that's nice about doing it in an RDD context is that you don't necessarily have to have this parametric likelihood-based selection model. It ends up being really tricky unless you have thousands of studies. So we actually did try it with, because we did simulations where it just does a very bad job of really identifying the size of the cutoff in practice. We did try it with, there's a nice corpus of something like 2,000 point estimates from the psychology literature. And so we tried fitting it there, and it still was pretty hard to identify the size of that cutoff. And of course, corpuses like that are typically not, it's a little bit hard to kind of figure out what the sampling frame really is and kind of what the applicability is. So far it's been a little bit tricky just in terms of sample sizes, but yeah.
Well, there is a paper, I can't remember the site, that suggests there are negative effects. And the argument is if you can get people who would be aggressive spending all their time playing games, then they don't have any opportunity to be aggressive. And so
Right,
like,
right,
this is
right.
what we want to do, is
Yeah.
actually get them to spend all their time playing aggressive games, and then
Right.
they won't be bullies at school.
They don't have money to buy things, but we don't allow them to be aggressive either. Only play video games.
Yeah, yeah, no, that's true. I mean, so I think like if that were kind of, I mean, and I'm not an expert on that literature, but if that were kind of a scientifically marketable finding that we're also selected for in the literature, then, you know, probably we would be looking at some degree of two-tailed selection. Again, these analyses would be conservative with respect to the point estimate, but I agree that that is, you know, certainly a possibility. The papers I've read have usually sold their negative findings more as like, this is not evidence for the suspected detrimental effects, not so much, look, we found that you can, you know, fix the aggression by giving people home video games.
That's the selection effects of professors into public health, which is much bigger than these.
Yeah.
Yeah, so working papers have their own publication bias. Would it still be able to exploit the fact that some of these papers come out in working paper form to get, you know, improve the estimates somehow?
Yeah,
And
that's.
also maybe address some of Gary's concern in terms of delaying publications due to quality or change in
Yeah.
framing?
Yeah, that's a great point. And so what you can do is you can include the unpublished studies and basically just upweight them along with the non-affirmatives, because those are considered to be a random sample of the latent population. Now, the thing that gets really tricky is that it's sort of hard to tell to what extent unpublished studies really are immune to publication bias. So, I mean, for instance, like dissertations, I mean, I don't know, because probably most people are planning to publish it, and so probably there's still, you know, selective reporting and influences like that. I do think that one case that's kind of special is registered reports, which is an idea that's kind of taken off in experimental psych lately, which is where you actually have your paper formally accepted for publication based only on sort of the protocol, and then it gets published no matter what. So I think that is one case where I would feel pretty comfortable saying this really doesn't have publication bias. Otherwise, I think I would be pretty conservative about trying to include those studies, because if they are subject to publication bias, they're going to make the analyses anti-conservative. So I would want to only include studies where I think there really is a strong rationale that there's no publication bias.
Could you use them as a first step somehow to get a better estimate of? I'm not sure about working papers, whether you upload something that is not significant in the way, the direction you're looking for, but
yeah, it's
at least
tricky.
we'll give you a sense of what's going on in the literature pre-publication.
Yeah, no, and there was actually a really interesting, I agree that that's a really interesting process, and there was a paper published in Science recently by Franco et al., where they actually did kind of a cool cohort of studies that were funded under this one particular kind of grant mechanism, and they actually followed them prospectively forward in time, and they looked at kind of at what point does the attrition happen. And so it's kind of cool because they found that actually most of the attrition is happening at the stage of people choosing to write things up. And so they actually, it seemed that it was less kind of the journals, or even like once something's been posted as a working paper. So I guess I would be a little bit worried based on that kind of thing, that people aren't even going to bother to write up the working paper if it's not significant. Or kind of what Gary said, where they'll just change, you know, they'll write it into something else, for example, which basically creates the same process.
Yeah, it seems like selection happens like early on, right? Okay, if you're a really good researcher, you basically have a good hypothesis and you have a better study to identify that fact, right? So if you're not a very good researcher, you probably have a horrible hypothesis and it turns out to be really bad. And then you get eliminated from the profession, right? So it's like, no, right? Yeah. So the selection process really, even the pre-registered designs, like if you're a really good researcher, you probably have maybe conducted already some pilot studies, so you have a good sense of what's going to happen. So it's unclear to me, like that distribution would probably be also skewed.
Yeah, but
that's
as a
interesting,
researcher,
yeah.
you're part reacting to how you think the journals
Right.
react, right?
Yeah.
So,
Unless we are so
you don't see
incompetent,
selection at the journal level, but that sometimes
right?
it
Unless
is
we are
there.
so incompetent that we are just randomly shooting, you know, hypothesis. So.
Yeah, I know that's interesting. Yeah, because it could be that that you sort of already like pushed around a little bit and you kind of think this is going to work. Yeah. Mm-hmm.
And then this, I mean, just to finger on this, this also, I think, gives you like a data engineering process of what Gary's talking about in practice, which is that these registered reports are situations where, you can't do p-hacking, you can't do any of those things. What you can do is choose the analyses that you're going to do that you think are going to be well powered, that you know from prior experience that you think are gonna be able, like actually gonna get you a publication result and things like that. And if you
Pre-hacking.
yeah, it's like, like you like choose to ignore all the things that you think now will not get you.
P-hacking.
Yeah.
Still P-hacking.
And that would be, but
Yeah.
I think that's just like give like an empirical example of like of the difference like in the data engineering process that would actually occur between the bad stuff and I think what Gary's talking about, like that would be the good way of doing things, even if without any kind of.
Well, so what would we want the researchers to do? Like, I really want them to keep looking until they find something surprising and then to come to us, right? So in some sense, it's look for the p equal 0.05, right? Like,
Yeah.
don't show me all the junk. Almost all experiments fail because somebody makes a stupid mistake, right? If you've ever run an experiment, I mean, you know, you asked the wrong question. You know, I once asked a question in Mexico, which went something like, okay, so Allison is quadriplegic, is in pain all the time. How much trouble does Allison have getting around the house? You know? And 15% said no problem at all. You know, I mean, so usually, most of the time we just sort of screw stuff up, and then if we eventually find something. The other thing is, like, what's the right way to run an experiment is, if feasible, is not to collect all the data, have everything pre-registered, run it all and wait for the big report and see what your answer is. The right way is run it with 3 people and then maybe 5 and then run it again and then fix things and then run it with 10 and run it again and keep doing that until you figure out what's going on. So you're pre-hacking or whatever it is. And at that point, then you run the big one that you can convince everybody else with.
Yeah.
And you know, so maybe a good researcher always produces p equal 0.05. But the estimate is actually a smaller number. So maybe that's okay.
The estimate of.
Well, I mean, suppose a good researcher could always produce p equal 0.05, right? You just have to, like if you did a sequential hypothesis test, so you could definitely produce p equal 0.05 if you sample long enough.
Yeah, so I think currently sort of the best practice model in experimental psych, which is kind of what I also try to follow in empirical research, is that you definitely do the piloting, and that's sort of described in an iterative kind of pre-registration process, but then there's a clear line between piloting and real data. So once you're done piloting, you throw out all that data and it's over and you have to start over for the real collection. Now, it certainly doesn't change the fact that like you potentially change the measures and things to try to measure things better, and then potentially that affects your point estimate. In a way that's, as you say, good, because you're actually measuring it better.
Yeah, and you also know, you basically, with pretty high probability, you know you're going to get p equal 0.05. Right.
Yeah, so you're kind of going at it with a question that's been framed to produce the right kind of results.
And you've tested it out.
Yeah.
Well, you want to make sure you commit to what's the pilot, though, right? Because otherwise, you're back into essential pre-hacking. No, psychologists do all that. I ran the experiment and the manipulation wasn't, very strong. I'm going to redefine the manipulation so I get stronger manipulation. Oh, now I got the result that I want.
So your point is that at some point you got to actually make yourself vulnerable to being proven wrong. Otherwise, what are you doing?
Right, and I think part of like one way that you can just like guard against Gary's like general thing here is that if the meta-analysis is very specific about this particular quantity of interest, I think this idea about you being able to hack your way in, like good researchers can hack their way in, can like do it, is much harder argument to make. Because what you're saying is essentially, I can refine the question. I can refine like the question, the measures, all of this stuff until the point at which I know that I found the true, like the one good question to ask that definitely has a positive effect.
And also, I don't remotely object to that. I think that's good.
No, I know that's good. But if the meta-analysis that she's studying are all just like, okay, no, ignore all that and just focus on everyone that is asking that same question now. So now all that variation should be just bad stuff.
Yeah, to some extent it does restrict it, yeah. Although, I don't know, it's been interesting because I do a lot of work also in replications, and it's so interesting how you can recruit 20 really great labs, tell them all to follow exactly the protocol that was in the specific paper, study 6, and you get heterogeneity. And you really try to get everything exactly the same, and it just still, there are things that we don't know affect the results. But I mean, I guess those are also the kinds of things that are harder to hack, in the sense that like if we just really don't know what they are, then maybe it's harder to kind of try to pre-hack them.
Well, I think the point is right. Is the last study you should do always should be a replication. It
Of your own
reproduces,
work,
you're replicating your last
Oh,
pilot.
yeah,
You think you got it
yeah.
right,
Yeah, that's right.
but no, she's telling us we have to throw away all the pilot data.
Well, I mean, that's clearly like,
And then replicate.
throwing away the pilot data is helpful to make yourself vulnerable to being proven wrong, but it's also like utterly the wrong thing to do from like a Bayesian perspective, right? You know, like you're throwing away information, like what, that's what we don't do in statistics, right? So, I mean, you were wrong with both. Right?
And your measurements and models and always probably affected by the previous studies anyway.
Yeah, that's
right?
true, that's
So
true.
you might be throwing away the data points.
In
but-
fact, good research, if you're doing a really good job, it will be.
Right, you should be.
Yeah.
It should be, right?
I mean, and I think
Which
like,
means statistically you have to pay attention. That's interesting. So, sorry.
and I think you certainly could, and I've seen this, like people embedding that in a formal Bayesian framework where you actually like account for the fact that you're basically doing a sequential trial design. I'm like more in the experimental psych world where data is super cheap, and so rather than doing that, it's easier just to throw out the pilot data. But I mean, I think there definitely are like principled ways